Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Hi, Mr. Wizard.
Oh, hi, Rita. Come on in. Hi. See that wheel?
Yes, it's turning all different ways, the lines.
As I change the little handle back here, you see how it happens to all those little things, see?
Yes, one go one way, and then the other lines go another way.
And in reality, that's not true, because here, I'll stop it, and you'll see that these are marks on a wheel. And notice if I start it very slowly, they're all going in this direction. See that?
Yeah, they're all going one way.
All going in the same direction. And yet, when I pick up the speed a little bit, there, you see how some of them are going the other way. And, of course, they are not. So this illustrates the kind of thing that you and I are going to investigate today. We're going to investigate illusions that are all around us in everyday life. Now, what does that mean, illusion?
Illusions is something that you see, but it's not really what it's supposed to be seen. Like, I saw it going the opposite way, but it wasn't really going the opposite way.
Well, that's an optical illusion. But the kind of illusions we're going to talk about today are not only optical, but other kinds of illusions as well.
Are there other kinds?
Yes, there are other kinds. Well, you have other senses, and so if you can fool those other senses, that, according to my definition, is an illusion also. Well, before we begin talking about illusions, let's look at these things over here. And notice the various ways that you can describe them, because I'm going to have illusions about show you illusions about the various aspects of these things. See these two little houses? Look kind of like toadstools and things? Well, how could you describe those? You could describe them by their height, right?
By their height.
Weight.
Their weight. Their color.
Their color. Their volume.
Depth.
Their motion.
When they move,
if they're moving or not. In other words, what I'm going to try to do is to design illusions that have to do with each one of these qualities: depth, height, weight, color, and so forth. Okay. Let's start with the first one. Which of these two little houses do you think has the most room?
Most room?
Yes.
Oh, I'd say this one right away.
This one?
But wait, you're always filled with tricks.
Yes?
They're probably equal,
Oh, but now, wait a minute. I know that if I'm going to tell you that we're going to do illusions, and I put together something, I know that you're going to think that I'm tricking you, and therefore I might do just exactly the opposite.
Then
knowing that you're going to think I'm tricking you, I will do just exactly the opposite of what you think. So you better be very careful.
I think I'm going to stick to what I first thought.
Well,
I think that has the most volume.
Even if you think it's a trick, this one certainly does look bigger, doesn't it?
Yes, it does. Looks like it has more volume.
More volume. Okay, now how are we going to prove it?
Measure it. We could measure it.
You could measure
find out what the volume of each one is.
And use the formula for figuring it out. And, of course, then there's this glass of water. Does that suggest something to you?
Well, it has little measure things.
Remember Galileo and his method of figuring out the volume of something?
You put this in there and find out how it goes up?
He took objects and put them in water, and how much water they displaced gave him an idea of how much volume there was. So let's do that. Let's take this little object, the top part, and put it in here. And notice that along the side here are marks.
Yes.
And the glass is of uniform shape, so that each one of those marks indicates a certain amount of volume, all of them equal.
All of them are equal.
Okay? I have a little thing in here so I won't splatter.
Okay.
Notice the volume of the first part.
Well, it goes up one to the next little measure.
To the next mark. Now I'll take the bottom part.
Well, that goes up a measure, too. I suppose they're equal.
That means that both of those were exactly the same volume, yes. In fact, let's try the next one.
That should be very... It's only another disc.
Yes.
Another little measure.
And look, in fact, look at this one.
Another one. That means they're all equal?
That's right. They're all exactly the same volume. This...
I should have said equal.
You should have said equal, because that time I fooled you twice. I made you think I might be fooling you. The point is that you could have put any combination together that you wanted. This, and they all are exactly the same volume.
Even though their shapes are different.
Even though their shapes are very different. These objects were designed in such a way so that they're all 1 cubic inch.
So you wouldn't think of that with the different shapes.
So you see how this is useful now to a designer. If he wanted to design a package to make it look like there was a lot of it, he might design a package that looks like this. If you wanted one that looked flat or something, he could design it this way.
I see.
Or,
So different shapes, but the same amount of
all it would
volume.
have the same volume in it. And scientists realize that your eye is fooled by this, so that they very carefully judge the volume either by measuring it and using the formula or using displacement, such as we did. Okay, now do you get the kind of illusion
Yes,
that I'm
that kind
talking
of
about?
illusion, yes.
That was the illusion based on volume. Now let's try area.
Area.
And in this case, I'm going to show you one of the illusions that I think is one of the best I've ever seen.
The best you've ever seen?
Because in spite of the fact that you actually make it yourself, you don't believe it. Right there. You see these two little wavy pieces of paper?
Yes, one's longer than the other.
Really? Now, point to them again. What did you say?
This one's longer than this one, because look at all that room there. Now you can tell right away.
Well,
that time,
yes,
because it's about an inch or so.
If that's the case, then when I take this one and put it up here, why, obviously... Which one did you say was longer now?
But I said this one was longer.
Yes.
No, this one is.
But now, will you please make up your mind which one of these is the longest? Because when I put this down here, you said that this one was longest.
But it is. You can even see
And when I put it up here, you say that one's the longest.
Maybe they're probably tricks.
They certainly are, because these are exactly the same size. Look. When you put one on top of the other, they're exactly the same size.
But how could they be the same size if we even measured? Look, right there. About
Okay.
that much difference.
Now, but before I explain why this happens,
They're
I
equal.
want to show you how you can make one of these at home. It's very simple, and I said, in spite of the fact that you yourself have made it, you won't believe it. Here's how you can do it. Get a piece of paper that's in a circle, and a paper plate, you know, like you use on
Yes,
picnics,
yes.
is very good. And you take a scissors, and you simply cut off the border all around the edge. And that gives you the arc, just as we have down here. And you can cut all the way around if you want, but I'll cut off only that much. Now you cut off a section of it, say like that. And you go ahead now and cut off those two sections that I just made. See, they're even on the end? You cut off both of them exactly the same
Exactly
length.
the same?
Cut them off exactly the same length. Okay, now
There,
didn't
now
you just
they're
do
the
that?
same. Right,
Okay,
now they're the same.
now measure. Put them down here side by side.
It got big again. Do they stretch? I mean,
It sure looks like it, doesn't it? It sure looks like
look
it.
at how much difference.
Yes.
Well, why does it
Well,
look so big?
this definitely looks smaller than this one. Well,
That's
now,
for sure.
here's why they do that. Look, if I turn this one around and put them together like this, notice they now look the
They
same
look
size?
equal now.
Yes. And yet, when I simply turn it around this way...
Well, does it grow every time you turn it that way?
Now, let's see if we can figure out why that is. This arc has a small section here, right? And a larger line over here on the top side.
Yes.
The top line is longer than the bottom.
Yes.
And what you're really doing is you're comparing the long side of one with the short side of the other.
Oh, I see.
And in order to
Instead of
line these
comparing-
up properly, you shouldn't make these two even. You should really line up this point and that point.
I
See?
see the two bottom marks.
Or the two top ones. And if you do that, then the illusion is this one still looks bigger.
It still looks bigger to
But
me.
that's one way that you can help minimize this effect. And of course, when you do it like this, then you see that they're
Looks
exactly
equal.
the same size. Now you see why I said that's one of the best ones I've ever seen?
Yes,
because
it is, because
in
it
spite,
really...
in spite of the fact that you've made it exactly the same size, you don't believe it. Well, now you could check the area of these two by putting them one on top of the other this way and checking it. Now let's give you an illusion in which you can't do that, but which you have to do some calculations to find out. Right behind you on the bulletin board there, you see those two circles?
Yes, two circles.
Here's one here, and here's one out here. I want you to tell me which is the biggest area.
Oh, well, right away, that's a silly question. And this one, of course, has more area than that. I mean,
Okay, but now you can't take this one and place it over that one because they're two
No.
different shapes. So you're going to have to compute which is the biggest area. I have a pad here and a pencil, and I assume that sometime in school you have had the formula for the area of a circle.
oh, yes, pi r squared.
Okay, would you write in big letters pi r squared?
Pi r squared.
Okay, now you can reverse that, can't you? R squared pi. It means the same thing.
Yes.
Okay, put r squared pi.
R squared
Pi. Okay. Now, would you put I down here equals?
I
I.
equals.
That I stands for this circle up here, inner.
Oh, inner
The
circle.
inner circle. So tell me now, how are you going to compute the area of this circle if I tell you that from the center here to the first line is 1 inch, this is 2 inches, that's 3 inches. So
That's
how are you
the
going to
radius.
compute it? The radius
well,
is what?
The rule says to square the radius. And if
Okay.
the radius is 3, the 3 3s are 9.
Okay, so the next,
Should be.
if you follow this formula, you would put down
That would
what?
be 9.
9.
That'd
And
be
just
9
put
pi.
pi.
I
Okay,
just put
9
pi.
pi.
9 pi.
So the area of that is 9 pi. Now, if you put O
Oh, for outer?
for outer,
Outer equals.
okay? Now, how are you going to compute the area of this? First of all, this is 1, 2, 3, 4, 5.
So the radius is 5.
Okay,
5
the radius of a large circle encompassing everything is 5 what?
That'd be 25.
Squared.
Squared.
Okay, so it's 25 pi. But that's the area of this whole circle. You have to subtract this one, don't you?
Oh, because we're only just measuring this
That's
one.
right. So what's the area of the part you have to subtract?
Well, that would be 1, 2, that'd be 4.
4
So
squared.
4 would be 16.
Okay, so 16 pi down here.
16 pi.
Okay.
And then you have to
You
subtract.
subtract those
So
two, and what do you got?
You have 9.
Pi.
9 pi.
Look.
Well, 9 pi. They're equal.
Yes. Doesn't that seem strange? That
How
both
does
of these.
that be equal to that?
Well, it just doesn't seem
possible.
right, and yet in this case, you have been much more scientific by actually measuring and computing, and they're exactly the same area. And you just proved it by doing the calculation.
Did I do it right?
Yes, you did. In fact, there's no doubt about the fact that they are exactly the same area.
So you really have to, just can't look at it. You have to find out by measurement.
So anyway, you see now I was able to show you an illusion that was based on volume, and another one now based on area.
Yes,
and
the area.
And in each case that you really had to measure in order to be sure what the actual situation was. Now let's try something else. How about trying, well, let's try weight.
Wait.
Yes. Come on around over here. Oh, wait, there, let's try the papers first. That's a good one.
Papers?
You see these two papers right here? Actually, they're piles of papers. One pile has 3 papers in it. They're ordinary writing papers. And the other pile has 4. And I want you to tell me by looking at it, I'll line them all up so that you can't count them, which pile is 3 and which pile is 4. Very simple.
Just by looking at it?
Yes.
I couldn't tell you like that.
In other words,
Just by
we're
looking
now
at it, you
talking
can't
about
tell.
we're now talking about depth, and a very, very slight difference in depth, and your eye can't do it at all.
No,
And yet
I couldn't do it.
you have a sense that we'll be able to detect the difference between one sheet of paper and 3 and 4.
My hands. You could feel
Try
it.
it once. I'll push these out here like this, and you feel one with one hand and one with the other, and see if you can tell me the difference between 3 and 4 sheets of paper.
Well, this one feels more.
Which
Feels
this
thicker.
pile feels
Yes.
thicker, therefore it
Feels
should be
thicker.
4,
It should be 4.
and this pile,
That should be 3.
now let's see if you're right. 1, 2, 3.
And that's probably 4.
This,
My fingers are pretty good.
1, 2, and this one is stuck together, and I can even feel the difference by, and 4. Now, doesn't that seem amazing?
Yes, my fingers are very
each one of
better
the-
than my eye.
I took a micrometer and measured the thickness of this sheet, and the thickness is 3/1000th of an inch.
3/1000th of an inch?
Yes.
You can do 3/1000th of an inch?
And you can tell the difference between 3/1000th of an inch by feeling. In fact, dentists use this system all the time whenever they're working with their little tool. Well, with those little tools, they can tell much more about the size and shape of the hole that they're drilling by the feel with their little
Oh, the feel
probes
of their
than they
little
can with by
instruments.
looking at it. Yes. So there is an example of depth in which your fingers were more sensitive than your eyes. Okay, now let's go to the one I was going to do in the beginning, which is weight. Here's a balloon.
Boom.
Okay, and here is a ball bearing. See?
Yes.
Would you put that in one hand and this in the other? Now, all I'm asking you to do is tell me which is the heaviest.
That's easy. Plus, the ball bearing is. The balloon has air in it and is very light. You can even feel it.
Oh, you think you're pretty smart, don't you? Wait till I prove it to you. That's heavier.
Which is heavy?
The balloon.
How can the balloon be heavy? Even feel it yourself. It is.
I agree, it feels it, but it's not
Right.
true.
Then how can you prove it?
Let's measure. Let's weigh it.
Weigh a balloon?
Weigh a balloon
Your
this. Here, I have a scale over here. You watch. This time you were positive you were right, and I'm positive you were wrong because I have already done it. Watch. Here's a scale. You
That's
see
not
it?
fair.
Watch. There's the ball bearing. You can see how this moves up and down.
Yes.
Wait, I'll stop it. It's a very delicate scale, as you can see, and you can see that it's almost the center, right? That's the weight of the ball bearing.
Right in the
Okay.
middle.
Now, if I take the ball bearing off and we put the balloon on. If the balloon is lighter than the ball bearing, what should happen up here?
If it was lighter, it'd go down.
Okay, and if it's heavier?
Well, then that would go up.
Okay, let's try.
It's going to go down, I'm positive. You must have done something wrong in your calculations.
I'll put the, squeeze the balloon in the side here. Okay, I'm going to let go. Here it goes.
Right
The balloon
again.
is heavier. The balloon is heavier.
Could the balloon be heavier than the ball? And you could even feel it.
In fact, it's quite a bit heavier. Look, I'll push it up and down. You see how quickly it goes
Yes, it
clunking
goes right
down?
up and boom.
Yes,
Balloon's heavier than that.
yes. Now let's see if we can figure out why you
I just can't
you
win.
were completely fooled on that one. Let me move this out of the way and I'll show you. When I asked you to tell me which one was heavier, I was really kind of cheating in a way, because what you really were going to do is you couldn't really tell which one was heavier using this system, because what you were reacting to is pressure. See,
Pressure.
all of the weight of this one, in spite of the fact that there's not as much weight here, all of the weight is concentrated in a relatively small area on your hand, right? Right underneath there. So the pounds per square inch here was fairly high as compared to, notice where the weight is here?
Well, it's all around my hand.
All around your hand. And therefore,
I
the
see.
pounds per square inch here was much less, and that's what you reacted to.
So this
Not
is
weight.
heavier.
That's right, not weight.
My hands aren't very good weight measures anyway.
What you have to use is these muscles up here, and of course you couldn't with this. So it's very easy to fool you with weight because
Oh,
of the
it's
pounds
heavier.
per
I
square
couldn't
inch.
get over it.
So now we've had weight, volume, and area. Now let's try depth.
Depth?
Yes, come here and close your eyes now. Close your
Close
eyes. Yes, close your eyes. Come around over here. Don't cheat now. And you turn around here, and you stand right like that.
Not my
Okay,
eyes.
about like that. Okay, now, don't open them yet.
No?
Don't want to turn on the
All
light
right.
here. Okay, now open your eyes.
Right there, open.
Okay, now what do you see?
I see balls.
How many? How many balls you see?
Well, there are 8.
1, 2, 3, 4, 5, 6,
2,
7, 8.
4, 6,
Okay.
8.
What
Yes.
color are they?
Well, they're red.
Can you roughly tell me the diameter?
Oh, about 2 inches, I'd say. 1 or 2 inches.
You know, every statement that you've made so far is false.
False.
Yes. Because you're looking in
Well,
this...
they're red. You can see that.
All right, except
And they're
that
balls,
part
and
of
they're-
it, but you said they were red balls, and that's false. You're looking in a mirror here, and the object is down over here. I'm going to pull the cardboard out of the way that I had in front of it, and you look down there now and see what you see.
What happened to the balls?
They're not balls at all. They're holes. Look.
Yes, but they were balls when I...
No, they were never balls. Ever. They're holes.
But how could it be a hole if it's a ball?
Well, let me see if I can explain what
I
happened.
just want to make sure
Yeah,
it's,
you put your
it's
finger
a
in
hole.
there and you'll see. You see, by putting these down here and painting them very flat with kind of a shiny paint and putting a light on them, I was able to create the effect that they were balls simply because of the highlight that went on the edge, and it could be either going down or up, depending entirely upon what you kind of suspected. And the minute you thought of them as balls, they became balls. So
I mean, they weren't really balls
they
at
were
all?
never. They were always holes. And scientists have to be very careful of this when they examine things like the moon or things through the microscope where they have no idea what they're looking at. They have to be very careful whether it's a hole or a bump when they look at something.
What are they
That's
looking
right.
at?
So therefore, I fooled you now this time with depth. All right, now let's take something that's relatively easy.
Easy? That's good.
Can you tell when something is straight up and down?
Oh, yes, that's one thing I
All
can
right,
do.
here. Here's a rod. See that rod? And it's movable. I want you to move it until it's straight up and down. In other words, vertical.
Well, that's not so hard. It's not hard at all. Think about that, be.
How do you know that's vertical?
Because vertical is straight up and down. I just
How do you
mean
know
it's
that's straight up and down?
I think it is. It looks like it.
In other words, you think your eye is pretty good for judging whether something is straight up and down or not.
I think my eye's pretty good.
Okay, here we go again. Close your eyes.
Oh.
Close your eyes. Now keep them closed. All right, now walk this way. Okay, there's a cable on the floor. Step up. Come around. We're going around the edge of the table now. Now turn around over here. Keep your eyes closed now. Keep your eyes closed. Okay. Now I'm going to position you in such a way so that you're looking at something, and I want you, when you open your eyes, to move your head and everything until everything is straight. Okay, go ahead.
Okay.
Open them up. Now move your head and everything until everything is straight, just like you did before. Okay.
Yes. Now that's just
Okay.
straight
Now, in other words, I tilted your head before. Now you straighten it all out till it's absolutely right. Is it straight now?
Yes, now it's straight.
Okay. Now, you sure everything is straight? You said you could tell when something was straight.
Yes, that's one thing I can do.
All right. Now here is a glass of water which I'm going to place in this room. And you know very well that when a glass of water sits on a flat surface, it's got to be flat. And look what happened.
What kind of water is that?
It's just plain ordinary water.
But it's all crooked and everything.
Are you sure the water can't be crooked? You know water always seeks its own level and is straight. I think you're a little nuts myself.
What kind of, is that water some...
No, it's plain ordinary water. See?
Well, then why is it crooked?
Well, that's because you don't know what you're talking about when you say that something is straight.
No, but I can't be
In
wrong
fact,
again.
yes, you can. Wait, I'll take the glass of water out of there. And you know a pendulum? You know how scientists and engineers and carpenters use pendulum to find what's straight up and down?
Uh-oh.
Here's a pendulum.
It's
Look
not
at it.
very straight, though.
There's a pendulum. Watch. In fact, I'll swing it.
It's not going very straight.
Now, you know when you swing a pendulum how it goes on equal distance on each side of center?
Yes.
Well, now, what's the matter with you?
What happened to the equal distance?
Yes. In fact, look. See how it's
Probably
kind of
another
lined
trick.
up about with one side of the window when it's only going in one direction.
Maybe you just have a magnet on one side, and has a magnet
In other
somewhere,
words-
and, you know, the magnet's pushing it
No,
over.
no. What happened here was that I have put you in a position where I have been able to fool you into thinking the vertical is not really vertical at all.
That's not
Yeah.
vertical?
Now, I had you get very close here so that you had to make references just to the room itself. Now, slowly back up and keep one eye closed and open like now. Slowly back up and you'll see what happens here. Because what I had done was to take this room and make it out of paper, and I put it on this thing and I tilted it slightly. You see?
Yes, it is tilted.
You see how it's tilted? And what you did when you looked in here, you automatically moved your head to straighten that out.
Oh, you mean I did it?
You did it.
I did. It's all my fault.
You see, because ordinarily you think of windows as being vertical, up and down, don't you?
Yes.
So when you looked into
Those
this
are crooked
room,
windows.
you straightened them out automatically. In your own mind, you said, well, if those are windows, they must be straight up and down. And, of course, when I put the pendulum, now you can see the pendulum is swinging properly,
Yes, now
can't you?
it's straight.
And
So it was the pendulum that was straight and the windows.
That's
were
right.
crooked.
In fact, here's the water that I put in, you see? Now you know
Yes.
the water is straight, you see. But, and the room is crooked.
Yes, it's
And
the
this-
room that's crooked.
And this is like the fun houses at the fair, you know, where everything's tilted at
Oh,
an
yes,
angle and you try
everything's
to walk
tilted.
out.
When you go in, you walk on a slant.
So now come back around over here to that stick over there. And how did you know that this was vertical?
I think I know it now.
What?
Well, this is vertical, and I had to get something else to make it look vertical, so this is vertical.
Yes,
I
you-
take it for...
You assumed that this
I
was...
measured it up.
You assumed that this was vertical because you assumed that this was horizontal, because you assumed the floor was horizontal.
Yes.
You assumed the walls and the bookcases and everything else are all at right angles, and therefore you lined up with them. And if we can tilt the whole room...
Then I probably
you
tilt that,
tilt
too.
like this, too. So even finding vertical is very difficult without actually measuring. And what do they use for that? Levels and
measuring?
plumb bob. Yes. Well, now let's do something with motion.
Motion.
Yeah, we've measured
Moving
things like verticals and areas and volumes and so forth. This time let's do something with motion. Here's a car, which we'll put there, and here's a street. We can have the car going down the street, see?
All right.
This is a street which I drew, so it's not too good, but at least I think you'll get the idea. Now notice that if I push the car along here, you can tell that it's moving. How come?
Because the background is moving, and also I can see...
No, the background's not moving, the car is.
Well, you can see... It looks like it's moving.
looked like the
It looks
background
like
is moving.
You can see a tree and
Okay,
then
and-
buildings.
And I watch what happens when I back up. Same idea,
Yes, and
right?
the buildings in the back go a different way.
Okay, now if I put the car here,
Mm-hmm.
whoops, this car has a spring on it. So. Now watch.
It looks like it's moving along.
Yes.
And it's past the trees.
Now
and
watch, it'll
everything.
back up. Now you know it's not. You see those little marks on the wheel?
Mm-hmm.
Now watch the wheels. It's not moving, yet you're almost positive that the car is moving. You see that?
They're not moving at all.
No.
Just the background is moving.
No,
But it looks
better-
like it.
Now I can make them back up. Go forward and back real fast.
Going to get a speeding ticket.
Because it's the background that's moving. Okay, now what happens if I move both at the same time?
I suppose nothing really would happen.
Well, watch. I'll move the car and the background both at the same time, and you get the effect of no motion at all.
I was right once.
Yes.
Once.
In fact, when a car is parked next to the curb out in the street, that's exactly what is happening. The Earth
How's that?
is moving, and so is the car, but at both the same rate, so you get the effect of no motion.
Oh, so you get no motion.
Yes.
Yes.
So
'Cause they're both moving.
even with motion, you can't tell. There are illusions all around you. And now, do you remember that illusion that when you go to a movie or you watch on television, the stagecoach going and the wheels go backwards?
Yes, the wheels go back.
Well, let
and
me see
forth.
if I can show you that one with that motor that I had
The
over
motor
here.
when I came in?
Yeah. Let me get this one off and put on a wheel with spokes. Now, here's a wheel with spokes, yeah?
Like the wheel on a station wagon.
Yeah.
A stagecoach
A
station
stagecoach,
wagon.
And here's a motor back here that I can control the speed. Now, notice which direction the wheel is going to go in. You point with your finger.
What's going this way?
Okay, now you hold your finger right up there like that. That's the direction that the wheel is
Going
moving.
that way.
Okay, now watch. I'll gradually get it to go faster and faster, and you watch what happens.
All right. Oh, the spokes of the wheel, they seem to be going the other way.
Now they seem almost standing still. Now they're going backward. There. How come?
Well, it's still going this way, right?
The wheel is only going in one direction. It's going like this, but the spokes seem to be going backwards. Now they're slowing up. Now I can get them to even
It's only
stop.
one
You see that?
direction.
Now I can get them to stop. Now I can make them go the other direction.
Control yourself even though it's just going one way.
Let me see if I can explain this now. Here in the room, I have a lot of fluorescent light. And the fluorescent light is going on and off. In the same way that in motion pictures, the frames are, you see flashes
Yes.
of frames. Or in television, you see several, pictures. So if this spoke happens to be in this position when there's one of those flashes, and in the next time there's a flash, that spoke happens to be in the same position. The next time there's a flash, that one, you will see them absolutely standing still.
Because every time there's a flash, there's a line.
Okay, but what would happen if first you see one there, and the next time you see one there, and the next time you see one there, and the next time you see one there, you will think that the things are going
Start
backwards.
moving.
That's right, and so you can get them to go forward or backward depending on the speed with which you do it. And scientists and engineers use that principle of making, that stroboscopic effect it's called, with this wheel I was using when you came in. And with it they can check things, speed of phonograph turntables and other things like that. So you see, all kinds of illusions that can take place in depth, in height, in weight, in area, and
Motion.
and scientists are very aware of all these illusions. So how do they prevent them from taking place?
They
By
have to be
measurement.
careful. Yes,
By
the measurement.
very careful measurement. And in fact, using the illusion like this, they can measure the speed of a turntable. So next time you want to be very accurate about something, make no judgments. Instead, measure and calculate.
Watch Mr. Wizard is presented each week at this time by the Public Affairs Department of NBC News in cooperation with the New York University.
I know that if I'm going to tell you that we're going to do illusions, and I put together something, I know that you're going to think that I'm tricking you, and therefore I might do just exactly the opposite.
Then I better say,
Knowing that you're going to think I'm tricking you, I will do just exactly the opposite of what you think. So you better be very careful.
I think I'm going to stick to what I first thought.
Well,
I think that has the most value.
Even if you think it's a trick, this
Yes.
one certainly does look bigger, doesn't it?
Yes, it does. Looks like it has more volume.
More volume. Okay, now how are we going to prove it?
Measure it. We could measure it.
You could
and
measure
find
it
out what the volume of each one is.
and use the formula for figuring it out. And of course, then there's this glass of water. Does that suggest something to you?
Well, it has little measure things.
Remember
over there.
Galileo and his method of figuring out the volume of something?
You put this in there and
He-
find out
yes, he
how
put-
it goes up.
He took objects and put them in water, and how much water they...
Watch Mr. Wizard. That's what all the kids in the neighborhood call him because he shows them the magic and mystery of science in everyday living.
Hi, Mr. Wizard.
Oh, hi, Rita. Come on in. Hi. See that wheel?
Yes, it's turning all different ways, the lines.
As I change the little handle back here, you see how it happens to all those little things, see?
Yes, one go one way, and then the other lines go another way.
And in reality, that's not true, because here, I'll stop it, and you'll see that these are marks on a wheel. And notice if I start it very slowly, they're all going in this direction. See that?
Yeah, they're all going.
It displaced, gave him an idea of how much volume there was. So let's do that. Let's take this little object, the top part, and put it in here. And notice that along the side here are marks.
Yes.
And the glass is of uniform shape, so that each one of those marks indicates a certain amount of volume. All of them equal.
All of them are equal.
Okay? I have a little thing in here so I won't splatter.
Okay.
Notice the volume of the first part.
Well, it goes up one to the next little
to the
measure.
next mark.
The
Now I'll
next
take the
mark.
bottom part.
Well, that goes up a measure, too. Well, I suppose they're equal.
That means that both of those were
both of those
exactly
are
the same
equal.
volume. Yes. Back, let's try the next one.
That should be very... It's only another disc.
Yes.
Another little measure.
And look, in fact, look at this one.
Another one. That means they're all equal?
That's right. They're all exactly the same volume. This...
I should have said equal.
I'm going to have illusions about show you illusions about the various aspects of these things. See these two little houses? Look kind of like toadstools and things? Well, how could you describe those? You could describe them by their height, right?
Their height,
weight,
their weight, their
yes,
color,
their volume,
depth,
their motion,
when they move,
if they're moving or not. In other words, what I'm going to try to do is to design illusions that have to do with each one of these qualities: depth, height, weight, color, you know, and so forth.
All that.
Okay. Let's start with the first one. Which of these two little houses do you think has the most room?
Most room?
Yes.
Oh, I'd say this one right away.
This one.
But wait, you're
What?
always filled with tricks.
Yes.
They're probably equal, you know.
Oh, but now wait a minute.
One way.
All going in the same direction, and yet when I pick up the speed a little bit, there, you see how some of them are going the other way. And of course they are not. So this illustrates the kind of thing that you and I are going to investigate today. We're going to investigate illusions that are all around us in everyday life. Now, what does that mean, illusion?
Illusions is something that you see, but it's not really what it's supposed to be seen. Like, I saw it going the opposite way, but it wasn't really going the opposite way.
Well, that's an optical illusion. But the kind of illusions we're going to talk about today are not only optical, but other kinds of illusions as well.
Are there other kinds?
Yes, there are other kinds. Well, you have other senses, and so if you can fool those other senses, that, according to my definition, is an illusion also. Well, before we begin talking about illusions, let's look at these things over here. And notice the various ways that you can describe them, because